Imagine standing on the tarmac next to one of the most powerful jet engines in the world. It is taller than you are. The fan at the front is a spinning blur of metal, and somewhere deep inside that machine the air is hotter than molten lava. Parts of the engine actually run at temperatures a few hundred degrees Celsius above the melting point of the metal they are made from. If you took the same alloy and put it in a furnace at that temperature, it would turn into liquid. So why does the engine not just melt into a glowing puddle of metal under the wing? That question already feels a little unsettling. Now add one more twist. High above the Earth, that engine is not only dealing with extreme heat and enormous forces, it is also swallowing tiny grains of dust and sand in the air, over deserts, near volcanoes. And even at normal cruising altitudes, those particles drift silently in the atmosphere. They are sucked into the intake. They race through the hot core. And some of them smash into the very parts of the engine that are already sitting on the edge of what is physically possible. So what actually happens when sand goes into a jet engine that is running hotter than its own metal? Should that worry you as a passenger? And how can that engine keep working for thousands of hours without tearing itself apart? Right now, there are easily 10,000 planes in the sky. You might even be sitting on one while you listen to this. All of those flights depend on engines like the one we are talking about. To understand how they survive, we need to go step by step into the heart of a modern jet, using only our imagination. How a modern jet really makes thrust. Start by picturing the engine itself. The kind of engine we are talking about is called a turbofan. If you have ever looked out an airplane window before takeoff, you have seen the front of this engine, a huge circular opening with a giant fan filling almost the entire space. During takeoff, those fan blades push more than a ton of air backwards every second. Only about 1/10 of that air actually goes into the inner core of the engine. The rest flows around the outside in a big ring. The air that does enter the core is squeezed by a series of compressors. Imagine rows of blades arranged like the stages of a windmill, alternating between spinning blades and fixed blades. As the air moves through these stages, it is forced into smaller and smaller spaces. By the time it reaches the back of the compressor, the air is at around 50 times normal atmospheric pressure, and just from that compression alone, it has heated up to several hundred degrees Celsius. From there, the compressed air flows into the combustion chamber. Picture a donut-shaped space that wraps around the engine's center line. In that space, fuel is sprayed in through rings of tiny nozzles and ignited. The chemical reaction releases a huge amount of heat. The temperature of the gas can jump to roughly 1,500 degrees Celsius. At that point, the gas is extremely hot, under very high pressure, and it desperately wants to expand. Between this ring of fire and the outside world sits a forest of small airfoils called turbine blades. In order for the hot gas to escape out the back of the engine, it has to push its way past those blades. When it does, it transfers some of its energy to them. The blades spin, and they drive a long shaft that runs down the center of the engine, turning the compressors and that giant fan at the front. On takeoff, each high-pressure turbine blade is producing as much power as a racing car engine. There are dozens of these blades working together in the hot core. As the gas rushes through the turbine and nozzle, its pressure drops from around 50 atmospheres down to roughly 1. It expands many times over, and that expanding flow is what spins the blades at tens of thousands of revolutions per minute. If that sounds like a lot of moving parts, here's the simple picture so far. The inner core burns fuel and turns hot gas into shaft power. That shaft power spins a huge fan at the front. The fan moves a gigantic mass of air backwards, and that air pushes the plane forwards. It feels backwards. But what really drives everything you see at the front of the engine is what is happening deep in the back. As the hot exhaust gas shoots out of the rear of the engine, it also pushes the engine forward. That is thrust. But here is a surprising detail. In a modern passenger jet, that hot exhaust from the core only provides less than 1/5 of the total thrust. The other 4/5 comes from that big fan at the front. Remember that only about 1/10 of the air was sent through the core. The other 9/10 bypass the hot section entirely. The fan simply grabs this cooler air and throws it backwards through a large duct that runs around the outside of the engine. The fan pushes this air back, and the air pushes the fan forward. In a sense, a turbofan is like a huge propeller wrapped in a tube, with a jet engine hidden inside to spin it. Why design it this way? Why not send all the intake air through the compressor and combustion chamber, like some fighter jets do? The answer is efficiency. Why modern jets are so big? The push that moves the plane forward comes from changing the momentum of the air going backward. You can get the same push by taking a small amount of air and throwing it backward very fast, or by taking a large amount of air and pushing it backward more gently. The momentum change can be exactly the same, but the energy cost is not. The kinetic energy of the air depends on the square of its speed. So if you double the exhaust speed, you do not just double the energy in the airflow, you multiply it by 4. A lot of that extra energy is simply wasted as very hot, very fast exhaust. So if you want an efficient jet engine, you want to move a large mass of air with a relatively small change in speed. That is what the giant front fan does. Over the years, engines have grown larger, and their bypass ratio, in the amount of air that goes around the core instead of through it, has increased. All that extra cool air flowing around the outside also helps muffle the noise of the hot exhaust. So far, our story has been about air and momentum, but there is another key factor in efficiency, and this one is all about temperature. The brutal temperature game inside a jet up, where jets cruise, around 11 kilometers above the ground. The outside air can be around -50 or -60 degrees Celsius. Inside the combustor, the gas can be hotter than 1,500 degrees. That temperature difference is what allows the engine to turn heat into useful work. In thermodynamics, there is a theoretical upper limit for any heat engine, called the Carnot efficiency. You do not need the exact equation here. In simple terms, the bigger the temperature gap between the hot side and the cold side, the more of that heat you can, in theory, turn into useful work instead of wasting as random thermal energy. So how do you make a jet engine more efficient? There are two obvious levers. You can fly where the air outside is colder, or you can raise the temperature inside the engine. We already fly where the air is very cold. So engineers have spent decades raising the temperature inside the core. That improves efficiency, but it also turns the interior of the engine into one of the harshest environments any machine has to survive. To keep a turbine blade intact inside that engine is a bit like putting an ice cube in an oven on its highest setting, leaving for a full workday, and somehow coming home to find the ice cube still frozen. It sounds impossible. Let us pause and spell out just how extreme this is. The blades sit in a gas stream that is hotter than the temperature where their alloy would normally melt. They are spinning incredibly fast, with the tip of each blade moving at nearly 2,000 kilometers per hour. Each blade wants to fly straight outward, but it is forced to move in a circle. Something has to supply the centripetal force that keeps it on that circular path. If you take a typical high-pressure turbine blade and calculate the inward pull required at full speed, it comes out roughly equal to the weight of 2 fully loaded city buses, tugging on that single blade all the time while it is glowing hot. On top of the mechanical load and the temperature, oxygen in the air wants to attack the metal and form oxides. The gas flow is laced with dust, sand, and other pollutants that can erode surfaces. Somehow, those blades have to withstand all of this for tens of thousands of flight hours without stretching too much, cracking, or breaking. So the next natural question is, what could you possibly make them from? Why normal metals just are not good enough? A natural starting point is ordinary steel. In a laboratory test, a steel sample under load behaves well at room temperature. When you pull on it, the atoms in its crystal lattice are stretched a little, but they stay in place. The sample gets slightly longer, but if you release the load, it snaps back to its original length. That is elastic deformation, and a certain amount of it is acceptable in an engine. As you raise the temperature, the picture changes. Atoms gain more energy and start to move more easily. Inside the metal, there are tiny imperfections in the lattice called dislocations. Under stress, those dislocations can glide through the lattice. At moderate temperature, they move slowly. At higher temperature, they move more freely. Once they start to move and multiply, the metal begins to deform permanently. The sample slowly stretches under constant load. That slow, time-dependent plastic deformation is called creep. Here is a simple way to picture it in your mind. Imagine a raft of soap bubbles packed together on the surface of water. They naturally form a hexagonal pattern. If you look closely, you can imagine places where the pattern is not perfect, where there is an extra half row of bubbles. Those are like dislocations. When you gently pull on the raft, those defects can move, and whole rows can slide past each other. The overall shape changes, even though you did not tear the entire raft apart at once. In hot steel under load, billions of dislocations are moving around in a similar way. The hotter it gets, the easier they move, the softer the metal becomes, and the faster it creeps. At some point, the cross-section thins out. The remaining metal can no longer carry the load, and the sample fails. What about titanium alloys? Titanium is roughly half as dense as steel, so a titanium blade would be much lighter. That would reduce the gigantic centrifugal forces it experiences. At moderate temperatures, titanium looks very attractive. But as you push the temperature higher, its strength also falls away. It too starts to creep and then fail. Early jet engines actually used steel blades and simply ran at lower temperatures. That made them less efficient, and they could only operate for a limited number of hours before the risk of failure became too high. Switching to a metal like tungsten, which has a very high melting point, creates a different set of problems. Tungsten is extremely dense and quite brittle. A tungsten blade would put even greater loads on the parts that hold it in place, and making complex shapes from it would be very difficult. You can optimize for melting point, or for strength, or for weight. But a turbine blade demands all three at once, and pushes each of those variables to an extreme. So where do you go from there? The strange alloy that gets stronger when you heat it. The solution engineers found is a class of materials called nickel superalloys. These alloys did not appear fully formed. They were developed step by step over decades by adding small amounts of different elements to nickel and watching how the metal behaved at high temperature and high stress. Early nickel alloys, with additions like chromium and cobalt, could handle gas temperatures a little higher than steel and keep their strength for thousands of hours. That was already a big improvement. But the real magic lies in what happens inside the alloy at the microscopic level, especially when you add a bit of aluminum. Imagine, just in your mind, that you could zoom in on this alloy with an electron microscope. The microstructure would look like a tiny city seen from above with blocks separated by narrow roads. Both the blocks and the roads are made from mostly nickel with some aluminum. But the atoms are arranged slightly differently in each region. In the road regions, called the gamma phase, nickel and aluminum atoms can sit in almost any of the lattice sites. There is no simple repeating pattern from cell to cell. In the block regions, called the gamma prime phase, the arrangement is highly ordered. Aluminum always takes certain positions, nickel takes others, and that pattern repeats perfectly. Why does that matter? Because this small difference has a huge effect on how dislocations move. In the gamma phase, the for and Shanshek, a dislocation can glide fairly easily. Layers of atoms can shear past one another and leave the structure looking more or less the same. In the gamma prime blocks, trying to shear the lattice would scramble that perfect ordering, putting atoms into the wrong sites. That costs energy, so the lattice resists it. So, when a dislocation traveling through a softer gamma region hits a gamma prime block, it tends to get stuck. As temperature rises, atoms vibrate more, and something even more interesting can happen. Dislocations can split, cross onto different planes, and in some cases form paired structures that have to move together. These are called super dislocations. Creating and moving them takes a lot of energy. The effect is that, over a certain temperature range, adding heat actually locks up dislocation motion and increases the alloy's strength, even as steel and titanium are becoming weaker. If you remember only one thing from this part, remember this. In a nickel superalloy, the right kind of microscopic order makes it harder for the metal to deform as it gets hot. Of course, nothing is free. If you made an entire blade out of pure gamma prime, it would be incredibly strong but also very brittle. One sharp impact or crack could cause a sudden catastrophic failure. The art of alloy design is to balance the fractions of gamma and gamma prime, and to sprinkle in other elements to tune properties like oxidation resistance and toughness. Modern nickel superalloys can contain close to 10 different metallic elements. Chromium improves resistance to oxidation and corrosion. Elements like cobalt, titanium, niobium, tantalum, and vanadium help stabilize the gamma prime phase. Molybdenum and iron can strengthen the gamma matrix. Rhenium, one of the rarest elements in the Earth's crust, slows down the atomic rearrangements that lead to creep at high temperature. A large fraction of the rhenium we mine ends up in jet engines, so now you have an alloy that can handle very high temperature and stress. But there is still another fundamental weakness in most metals: the hidden weak spots, grain boundaries. Nearly every metal object around you, from a spoon to a pen, is made of many individual crystals, or grains, stuck together. Where their lattices meet, they do not line up perfectly. Those boundaries are full of misfits, vacancies, and impurities. They are weak points where cracks can start and where atoms can move more easily, especially at high temperature. Under the enormous centrifugal loads on a turbine blade and in the presence of high heat, grains can start to slide along those boundaries. The whole structure can slowly deform like soft candy. As long as a metal has many grains and many boundaries, it will creep more easily. So engineers did not just redesign the alloy. They redesigned the crystal structure at the scale of the entire blade. The goal was simple and radical. Grow each blade as a single crystal, one continuous lattice from root to tip, with almost no grain boundaries inside it. How you grow a metal crystal sword. The process for doing this starts in a way that feels almost low-tech. In a casting facility, technicians inject wax into a precise metal die shaped like the final blade. A ceramic core is placed inside the die to create hollow channels later. The wax pattern that comes out has exactly the outer geometry the blade needs. Workers carefully remove seams, smooth surfaces, and inspect every detail because any flaw in the wax will become a flaw in the metal. If you picture someone icing a cake and slowly smoothing every bump and ridge with a spatula, that is the level of care we are talking about. Multiple wax blades are then attached to a central wax structure, forming something like a tree. This assembly is dipped into a thin ceramic slurry, then coated with fine sand. That layer dries and hardens. The process is repeated with thicker slurries and coarser sand to build up a strong shell. Once the shell is complete, the wax is melted out, leaving behind a hollow ceramic mold. The mold is fired to strengthen it and remove any remaining wax. Now imagine a vacuum furnace glowing with heat. The nickel superalloy is melted in that furnace at a temperature similar to what it will see inside an engine. The ceramic mold is heated as well and mounted vertically. The molten alloy fills the mold from the bottom up. At the very base sits a water-cooled copper plate, etched with small grooves. Those grooves act as starting points for crystals to form as the alloy begins to solidify. The whole mold is then slowly lowered out of the hot zone of the furnace. Solidification moves upward from the cold plate toward the tip of the blade. If you stopped here, you would end up with many long columnar grains aligned along the length of the blade. That is already an improvement, because there are fewer grain boundaries cutting across the main stress direction. But engineers discovered that by adding a helical passage, a spiral often called a pigtail, just above the chill plate, they could go even further. As the solidification front moves through this spiral, many of the competing grains are blocked by the walls or by each other. Only one grain, oriented just right, makes it through the entire spiral and into the blade section. Above the pigtail, that single crystal continues to grow, filling the whole blade. The result is a part that behaves, from a mechanical point of view, like one giant crystal. After casting, the blades are heat-treated again, almost up to their melting temperature. This gives atoms enough mobility to rearrange into the ideal mixture of gamma and gamma prime phases throughout the crystal. Even the orientation of the crystal matters. If the lattice is tilted too far away from the direction of the main load, the stresses inside the blade change, and performance suffers. With modern process control, manufacturers can successfully cast the vast majority of blades as single crystals with the correct orientation. Let us stop and recap what we have built so far. An alloy whose internal structure gets stronger when hot. A blade that is essentially one giant crystal, with no easy paths for cracks to run along. A shape that can survive loads equal to multiple city buses pulling on each blade. But we still have not answered the original question. If the gas inside the engine can be around 1500 degrees Celsius, and the alloy starts to weaken at somewhat lower temperatures, why do the blades not melt? For that, we need the final layers of defense. Cooling a blade that lives in fire. Think back to the ceramic core that was placed inside the wax pattern. After casting, that core is removed with a chemical process, leaving behind hollow passages winding through the solid metal of the blade. Compressed air taken from earlier stages of the engine, still very hot by everyday standards but cooler than the combustor gas, is routed through those passages. As it flows, it picks up heat from the metal and carries it away. Small holes are then drilled from the blade surface into those internal channels. Through these tiny holes, some of the cooling air leaks out and forms a thin film over the surface of the blade. That blanket of air insulates the metal from the hottest gas, a technique called film cooling. The surface of the blade is shaped with little ridges and features that make the flow turbulent, which helps that airstrip heat from the metal more effectively. On top of that, the blade is coated with a thin metallic bond coat and then a ceramic thermal barrier coating. Even though this ceramic layer can be thinner than a millimeter, it can keep the underlying metal more than 100 degrees cooler than it would otherwise be. Together, the internal cooling and external coating allow the gas flowing past the blade to be significantly hotter than the effective temperature at the metal surface. So now we have a superalloy that keeps much of its strength at high temperature. A single crystal blade with almost no weak grain boundaries, internal cooling passages and film cooling that create an invisible layer of protective air. a ceramic jacket that shields the metal from the hottest gas. At this point, it sounds like we have solved the problem. Strength, creep, oxidation, heat, all handled. If only the atmosphere were perfectly clean. What sand and dust really do inside a jet engine. In reality, even at cruising altitude, there is dust in the air. Over deserts and near volcanoes, the concentration can be much higher. When that dust goes into the engine, it does not simply pass straight through. In the hottest parts of the turbine, those tiny grains can partially melt and stick to surfaces. Over time, they can sandblast the coating, clog cooling holes, and build up glassy deposits that block the flow of cooling air. Once cooling is reduced, the metal runs hotter. The ceramic coating can start to fail, and the underlying alloy can be pushed beyond its limits. To find out how serious this problem is, engineers run full-scale tests on the ground. Picture a jet engine mounted in a test cell, spinning up to full power. Measured amounts of dust are injected into the inlet, sometimes only a few spoonfuls over an entire test cycle. Even those small amounts can cause noticeable damage if the conditions are right. The dust attacks the thermal barrier coatings and slowly undermines all the careful cooling and alloy design. This is why materials scientists and engineers are still working on turbine blades today. They are developing new ceramic coatings that are more resistant to dust and ash, refining internal cooling geometries, and tweaking alloy compositions to squeeze out a little more life at a little higher temperature. In other words, we are already at the edge of what is physically possible. And yet we are still nudging that edge outward. The everyday miracle under your airplane wing. So let us come back to you, sitting on a plane, looking out at that smooth spinning fan on the wing. Hidden behind it, out of sight, metal is enduring conditions that sound impossible on paper. It is running hotter than its own melting point, held together by atomic patterns with names like gamma and gamma prime, cast as single crystals, cooled from the inside by air that is itself hotter than your oven at home, and protected by ceramic films thinner than your fingernail. All of this is happening while the engine swallows dust and sand from the sky. The fact that these machines work at all feels like a contradiction, and yet they do. Every day, they carry millions of people across the planet, quietly turning the impossible into something so routine that most of us never think about it at all. The next time you feel the engines roar at takeoff, you will know that somewhere inside that metal, there is a tiny war going on between heat, stress, dust, and the limits of physics. And for now, at least, the engineers are winning.